Alrighty, here's our last recording. Alright, so we're talking about systems of differential equations, modeling competing populations, section 11.8. Okay, so take a look. You know what? Your homework tonight includes 5, 10, 15, 20. On this page, I'm going to basically do 5 and 10 with you, okay? Just to show you how this works. All right, and to do 5 and 10, you really have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's all one big messy thing, all right? So start with number 1. No, 2. For exercises 2 through 10, let W be the number of worms in millions. So W equals 2 means 2 million worms, okay? And R, the number of robins in thousands. So R equals 3 means 3,000 robins. Okay. Living on an island. Suppose W and R satisfy the following differential equations, which correspond to the given subfield. Okay. So you're given this. dW, dt, is equal to W minus WR. There's usually more constants of proportionality, but this is a simplified model, so that's fine. And dr dt is negative R plus WR. All right. My question is, it says number 2, explain why these differential equations are reasonable for the interaction of the two populations. Why are the signs chosen the way they are? All right, let's do this. What happens to the worm population if there's no robins? What if R is 0? Then this term that is proportional to how many times they interact, how many times a robin sees a worm, that kind of thing, okay? The more worms there are, the more robins there are, the bigger this number is. That's what this is. It's an interaction term. If R is 0, then you get this. Don't you? Okay. What does that mean? The W dt, the rate of growth of the worm population over time, is proportional, the constant of proportionality happens to be 1, to the number of worms present. What kind of model is that? We know 3 models. Logistic growth and decay, exponential growth and decay, Newton's law of heating and cooling. Which one? Exponential. Growth or decay? Growth. Okay, so is that a good thing? These worms live on an island. They can't swim, right? So what happens if this grows exponentially? What if the worms just go crazy and overpopulate the entire island? Is that a good thing for the worms? That's not really a good thing for the worms. Somewhere along the line, this model will crash. They're all going to die. They're going to run out of whatever the hell they eat. Okay? Okay. But look at this. This interaction term is negative. What does that mean? If R isn't 0, the rate of growth of the worm population, is it bigger than this or smaller than this? Smaller, so they keep the worms in check. All right, go over here. Look at the rate of growth of the robin population over time. What if there's no worms? What kind of growth model is this? Exponential decay. So they go extinct. Actually, they both go extinct. This goes to 0 because there's no food. They eat worms, right? And again, this is a positive. Look at this. This interaction term is a positive term, so that it may outweigh this extinction. It may help them not to become extinct, right? Because this is positive and this is negative. Okay. But these are both considered extinction models. As time goes to infinity, if this is what's happening, the population goes to 0. That's your basic extinction. This is a different kind of extinction. It's called doomsday. This is a doomsday model. You overpopulate the Earth, you run out of food, and it's over anyway, right? That's a bad thing. Okay? So this is also an extinction model. This is also bad. So for the worm population, the robins are good. For the robin population, the worms are good. Why? Because the robins, what do they do to worms? They eat them. I mean, that's their food. And the worms, what do the robins do? They eat them. But that's good too, because otherwise you go to doomsday. All right, so there's the fine line whether they're going to go extinct or not, but they help each other out. Okay. That's why it makes sense. Now, my second question is, where do they get this slope field from? How could you come up with the slope field yourself on your calculator? Well, look at it. Look at the bottom of the slope field. It says figure 11.6.2, right? Right there. See what it says? dr dw equals? Aha. They've gotten rid of the parameter t. That slope field doesn't have t in it. It just has r's and w's. Okay? If you divide, what do they want? They want dr dw. If you divide dr dt by dw dt, don't you get dr dw? Let's take a look at this. Okay, so just to be complete here, I'm 573, and this is 2 through 10, okay? This is just one big mess. Okay, if dw dt is w minus wr, and dr dt is negative r plus wr, what's dr dw? Isn't it dr dt divided by dw dt? Right? Remember when we did parametrics? Okay, so if you divide the w dt to the r dt, this is a fraction. How do you divide by fraction? Multiply with the reciprocal, the dt's cancel, you get the r dw, right? But what is that? The r dt is this, divided by the w dt is this. Is that what they wrote down there? Well, they factored out an r. If you factor out an r, you're going to get that. Factor out r here, you get 1 minus w, the w, negative 1 plus w, right, was what they have. And you factor out a w here, they got 1 minus r, same thing. My question is, can you use this with our slope field program and get that if they don't give you a slope field? Let's see. Now remember, our slope field program has y's and x's, right? And usually when we have a derivative and it's not y's and x's, we usually think of the top as the y and the bottom as the x, just by convention. So it's like dy dx. So in my program, r's are y's and w's are x's. That's all. Okay, so let's do that. Let's bring out Ziggy. And remember, before you run the slope field program, we got to do what? Go to y equals. Well, it would help to turn it on too. Y equals. Where are you going? Okay, let's clear that out. All right, now remember what we said. R is y in the program alpha y, and w is x, the variable x, right? So I'm just going to write this: negative y plus x times y in the numerator. Okay, so open parentheses, negative alpha y plus x times alpha y. That's the numerator where r is y, right? The denominator, let's see, w is x, so it's x minus xy. Okay, divided by, open parentheses, x minus x times y, alpha y. Okay, great. Now look at the window they have. The w's go from, the x's go from 0 to 4, and the r's, or the y's, go from 0 to 4. So set up the window the same way. I usually set up the window before you run slope fields anyway. So 0 to 4 by 1 is good, I guess. And 0 to 4 by 1 is good. All right, so run slope fields and see if you don't get the same slope field they have there. Except we have 12 by 8 lines. They have more, but it's going to be similar. All right, so there's my slope field. Okay, good. So question 2 was, why do those differential equations make sense, and where did the slope field come from? We're done with 2. 3, solve those differential equations in the 2 special cases where there are no robins and no worms. We did that too, didn't we? We said if there's no robins, you get this, and remember the general solution is, if you do variable separable for these, you get w as a function of time is w0 e to the t, or kt, but k is 1. And here r equals r0 e to the negative t. Isn't that the general solution we would get from variable separating this stuff? Haven't we done this enough times? Always the b is the initial amount, and this number is the k, right? The number in front of the r. All right, so we did that. I mean, that's the argument we were making for question 3. We did that already. 4, describe and explain the symmetry observed in the slope field. What consequences does the symmetry have? Okay, so let's go back to the slope field. Okay. Look what it is. It's cyclical. Now, this is not a square window. It might be circular. I'm not sure. But it's some kind of a cycle. Now, which way am I going? When I graph solution curves, if I ran Euler G here, and I got solution curves, I don't get r as a function of time. I don't get w as a function of time. I get r as a function of w. That's called a phase plane. This slope field is called a phase plane. And when we draw solutions here, we get trajectories. We're going to get a relationship of r versus w, right? This is the w axis, this is the r axis, right? The question is, if you follow along these curves, you get, like, I don't know, an ellipse or something weird, right? But which way does it go? Does it go this way? Does it go this way? Do the populations die out? Does something go crashing to 0? Does r go to 0? Does x go to, does w go to 0? I don't know. Well, let's find out. Number 5. What if w starts with 2, or 2 million worms, and r starts at 2, or 2,000 robins, at whatever t equals 0 the initial time is? Do the number of robins and worms increase or decrease at first? Why, and why not, or what happens? Okay, so if I start at 2, 2, what is dw dt? dw dt. If I start at the point 2, 2, w is 2, and r is 2. So here. What's the growth rate? What's the dw dt? Well, 2 minus what? 4. Right? Isn't it 2 minus 2 times 2 is negative 2? And the point is, that's a negative growth rate. Now remember, the w is like the x. So if the w dt is negative, and that's like the x's which go left to right, which way am I going? Left. Okay, so I'm starting, let's see if I can draw on this thing. I'm starting with an initial condition of this. Draw. Draw. It's not giving me a draw. There it is. You want to let me draw on here? I thought I drew on here yesterday. I guess not. Oh well. I did, didn't I? Yeah. It's not letting me. Whatever. The point is, at this point, we're going to the left. The x's are going left, not right. What about the r dt? That's negative r plus wr. That will be negative 2 plus 2 times 2. Negative 2 plus 4 is 2. This is great. This is less than 0. This is greater than 0. W's go left and right, so I'm going left. R's are the y values. They go up or down. So since it's positive, which way am I going? Up. Okay? So, okay, now, say this was a test question. What would I ask you to graph? I wouldn't ask you to graph all these millions of lines here. Okay, I'd ask you to graph the solution curve. All right, so how would you graph it? We'll go like this. This is the r-axis. This is the w-axis. This is the origin. This is 4 million worms. This is 4,000 robins. Initial condition, 2, 2. Initial direction for W and initial direction for R. What is the trajectory doing then? Where's my thing? If I'm here and I want to go up and left, I'm following this. Isn't this tangent line going up and left? It could go down and right, but I'm going up and left. All right, so how does it go? It goes up, 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 then it goes down, 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 then it goes up, down, and then it flattens out, then it goes like, right? Okay, imitate that here. something like that. That's your solution curve. Now be careful, you're not going to get that from Euler G. Why? If you run Euler G here, what's the problem? Do you see that some of these, well, it may not be obvious. Well, here it's obvious. Some of these slope lines are vertical. What kind of slope do you have on vertical lines? No slope, undefined. And remember that Euler's method uses the derivatives there. It's not defined. It's going to crash or do something crazy. So if I actually run Euler G on this, it might work for a little bit and then go nutsoid. So I wouldn't use Euler G on this. I'd eyeball it and just sketch it by hand. So I started here, and then over time I'm here, 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 then I'm back. I'm thinking this is like a whole year. This cycle is like a whole year, 12 months or something. So there's the time. There's W, there's R, there's the time. These arrows, that direction is what happens over time. We're going in this direction over the solution curve over time. Remember, we got rid of t by dividing dr dt by dw dt, so the t's were gone. But technically they're there in the direction that you're taking on this trajectory. Okay? So there's your solution curve. All right, so at first, do the numbers of robins and worms increase or decrease? The worms, what? Decrease. The robins, increase. Okay, 6. For the same case, estimate the maximum and minimum values of the robin population. Well, it started at 2,000 robins. How high do you think it goes? Roughly, how high is that? That's 2,000, what's that? 3,700 maybe? Not 4,000, right? Oh, sorry, wait. That's 3,000, right? That's 2,000, or maybe 2,700 maybe? Right? What's the minimum robin population? How low does it go? If that's 1,000, what do you think that is? 200, 250, something. We're just eyeballing it, right? All right. How many worms are there at the time when the robin population reaches its max? At the time the population of robins is its max at 2,700, what's the worm population? What's W for that point? 1 million worms. Okay. And, all right. What about the worm population? What's the maximum worm population? Over here. It started with 2 million, but eventually it becomes how much? What's the most that W gets? About 2.5 million maybe? What's the least that the worm population becomes? 500,000, maybe less, 300,000, something. You're just estimating, okay? Okay, on the same axis, graph W and R, the worm and robin populations against time. Use initial values of 1.5. Well, we did that for 2, all right. What if we perturb the system a little bit? Like, all right, look at number 8. People on this island really like robins. They like robins so much that they decide to import 200 more robins, all the way from England, to increase the initial population to 2.2 at t equals 0. Does this make sense? Why or why not? Well, let's make it really obvious, okay? What if we import 2,000 robins? Let's make it even better. We like robins, right? More robins the merrier. Okay, fine. So instead of the initial condition being 2,2, it's 2,4, right? Okay. Now, dr dt is still negative r plus wr. This point was 2,2, right? This initial condition here. This point is 2,4. So plug that in. What do you get? Negative what? 4 plus 2 times 4 is negative 4 plus 8 is 4 is still positive. So we're still going up. The R's are like Y's up or down. What about the W dt? Well, the W dt was given. It's W minus WR. W is 2 and R is 4. 2 minus 2 times 4 is 2 minus 8 is negative 6. That's negative. So now we're going what? Left. So it's the same initial trajectory. Up, left. Okay. What does it look like though? On the graph. Here's 2,2. Here's 2,4. It's way off the screen. I don't see it. Yeah, maybe we should make this window a little bit bigger. Well, the point is, okay, the point is this. Look what's going to happen. The trajectory is going to do the same thing. It's going to go up, then it's going to go down, and it's going to go flatten out and come back. Okay? If you had a bigger screen, you'd see that. All right, so over a 12-month period, let's say we end up back here. So that's good. We still, you know, the worms don't die out, the robins don't die out, and we end up with lots and lots of robins. That's a good thing, right? Because we really, really like robins. Right? So we start with 4,000 robins, but what's robin max now? It's about 5,000, maybe more. That's even better. Okay, so the question is, does this make sense? Why not? Would you really want to do that? If you really like these robins. Why not? There's no right answer here. One right answer is, yeah, because look, I can get 5,000 robins. I really like it. Okay, fine. Talk about R max. But wait a minute. Talk about R min. What the freak is R min now? It's lower than before. It's getting precariously low. It's going to be susceptible to other factors that are not in our model, like, oh, I don't know, a hurricane, you know, right? So they can start saying, well, you know, the minimum population is going way low. It's like 100 robins at one point. If that's like hurricane season, this could be bad. Because then those 100 robins get blown away, and then I got no robins, and I'm sad because I like robins is bad, right? So there's no right answer here. You interpret the graph, right? You interpret this graph in terms of the context of the question, but it has to do with the graph, doesn't it? So if as long as you're talking about what happens with this graph, and the graph is accurate, you know, pretty accurate, close, you know, pretty close to what I got here, right? You've got the right answer, okay? Same thing with worms, by the way. Worm max becomes almost 4 million, but what about worm min? It's less than before. Before it was like maybe 500,000, now it's maybe 250,000. Well, that's a lot of worms, I guess. But, you know, if you have a lot of robins, you need a lot of worms, that's a precarious population too for the worms. What if they die out? If the worms die out, remember, we get extinction for the robins. That's bad. If the robins die out, we get doomsday for the worms. That's bad. So you can talk about both mins being dangerous. That would be the answer here. Okay? Now, the point is this. You're using subfields to solve a system of differential equations. Two different differential equations involving two different populations that interact. That's a big deal. To do that analytically is incredibly difficult. And doing this with the subfield graphically is not too bad. All right, so that's what we want to practice now, okay? So any questions on how to use subfields this way? All right, let's try that again. Let's take a look at some of the questions from the same homework page. You've got 15. Let's do something like 15. All right, let's say, I guess, 17. All right? The systems of differential equations in problems 15 through 17 model the interaction of two populations x and y. In each case, answer the following two questions. What kind of interaction is it? Symbiotic, competitive, or predator-prey? By the way, this one we just saw here, robins and worms, what would you classify that? Predator-prey, right? Okay. This kind of cycle thing is predator-prey unless the predator dies out, right? Okay. So now let's see what we get, okay? So see if you have a symbiotic situation, a competitive situation, a predator-prey situation, and B, what happens over the long term? Is there like an extinction? Does one population win out over the other? That kind of stuff, okay? So let's do 17. Let's do the same idea. 17 says, okay, what does it say? 1 over x dx dt is equal to y minus 1 minus 0.05x. Okay? And 1 over y dy dt is equal to 1 minus x minus 0.05y. Now let's do the same kind of questions we did, questions 2 through 10, on the robins and worms. Let's do the same kind of analysis here. What's the growth rate dx dt? It's this. dx dt is equal to xy minus x minus 0.05 x squared. That's the dx dt by itself. What's dy dt by itself? Dy dt is y minus xy minus 0.05 y squared. Okay, what does that mean? What happens to the x population in the absence of the y's? What if y is 0? Then this is 0, yes? All right, so then you get dx dt is negative x minus 0.05 x squared. Isn't that a logistic problem? Remember when we have the rate of growth is a parabolic? The rate of growth of x is proportional to x squared. That's logistic. Okay? What about this one? What happens to the y population in the absence of the x's? This zeroes out. Okay? Now, what kind of logistics is involved here depends on the initial condition. Everything's negative here, right? This is a negative growth rate. Here, sometimes it's positive. This could be logistic growth while this is logistic decay. I don't know. So this will die out over time, won't it? If there's no y's, they're going to die out. If there's no x's, you could have logistic growth or decay depending on initial conditions. I don't know. So this population needs the y's to survive, doesn't it? Right? And this population doesn't really care. This might actually thrive. So what kind of interaction is that? Symbiotic, competitive, or predator-prey? This population doesn't care if X doesn't exist. This population dies if Y doesn't exist. Isn't this symbiotic? It's a special kind of symbiosis. It's there are a lot of different. Who's a bio major? Or who took AP bio ever? Nobody? Aren't there three kinds of symbiosis? There's mutualism. They help each other. There's parasitism. One doesn't care about the other, but one needs the other to survive. That's this, parasites. And there's a third one. Does that sound familiar? Or am I making stuff up? I'm not a biologist. Huh? Right? Commensalism? Commensalism? What's that? What does that mean? You know, mutualism is good for both. What is it? They don't really care. Okay, all right. So it's symbiotic relationship, but they could live without each other. Okay, so that's mutualism. Commensalism is good for both, and parasitism is the parasite needs the host or it dies. That's what this is, isn't it? X is the parasite. Y is the host. Okay. All right, so we know what it is. It's a weird type of symbiosis, but that's what it is. All right, and what happens over the long term? Well, let's graph the trajectory, the slope field, and see what it looks like. So what am I going to do? I'm going to do what am I going to do? I'm going to do dy dx. Let's do dy dx in my slope field program. Well, what's dy dx? Here's dy dt, y minus xy minus 0.05 y squared, over dx dt, before we got rid of the y's, this one, right? Xy minus x minus 0.05 x squared. By the way, notice how the interactive term here is a positive quantity, so it helps when y exists, and this is a negative quantity, so it's not that good when x exists. Actually, I guess the parasite might actually hurt the host, I don't know. So it's some kind of symbiosis, whatever. So let's graph this in a slope field. So I got to change y equals to this crazy mess. All right, so open parentheses for the numerator, alpha y minus x times alpha y minus 0.05 y squared, so alpha y squared. That's the numerator. Close it. Divided by, open the denominator. Okay, x times alpha y minus x minus negative 0.05 x squared. Did I copy that good? And I don't know if the window we have is okay. I'm going to keep the same window. If it's not good, we'll play around with it. Let's just run the program. All right, so just enter that. Okay. So program, slope fields. And remember the last window was 0 to 4, 0 to 4. I don't know if that's big enough. We'll find out. Enter. Enter. This looks the same. This looks like a predator-prey. Is this symbiotic or is it predator-prey? Look, it has components of symbiosis, but it also has the idea with the predator-prey where if this goes, this is a good, the growth rate, when it's positive, that's good. This is a positive growth rate here. X is positive, Y is positive, the product is positive. X is a population, it's got to be positive. Y is a population, it's got to be positive, right? So when we lose this term, that's bad for X. When we lose this term, since it's negative, it's good for Y. That has elements of predator-prey too. I don't know. It's hard to tell. Let's see what happens. Let's do some initial conditions. What if we start at 2, 2 again? What do X and Y do? Okay, let's find out. If I plug in 2, 2. 2 times 2 is 4, minus 2 is 2. Minus 0.05 times 4 is 0.2. So 4 minus 2 is 2, minus 0.2 is positive. X is positive now. So what's that? Up, down, left, right. Dx dt is positive, means you're starting to move right. Okay, what about dy dt? 2 minus 4 is negative 2, minus something is more negative. So dy dt is negative, that's up, down, left, or right? Down. Okay. So let's see this thing. So this graph almost looks exactly the same as the last graph. All right, fine. So let's draw it. So again, 0 to 4. You can have a different, X min, X max, doesn't really matter. This is your X population. This is your Y population. At 2, 2, we were going to the right for dx dt and down for dy dt. And then what did it look like? At 2, 2, it was sort of not quite so steep. All right, so something like this. Let's see, wait. Okay, something like this. All right, so I guess this is more like a predator-prey. That looks like a predator-prey. All right, so we start with 2, 2. We end up with a certain X max, certain X min, a certain Y max, certain Y min. It's the same kind of cyclic behavior. I'm going to say this is predator-prey. They help each other out. The populations help each other out. But you could get different kinds of solutions here. Let's see. All right, I don't want to do too many of these because then you don't have any left to do. So, all right, I'm going to leave it at that. So you can try that for homework. We'll go over those tomorrow. We did 5 and 10. You can skip that, but we'll do 15 and 20 tomorrow. Okay, so 15 and 20 is on the homework? All right. Any questions up to this point? What can happen is you could have some really weird slope fields. You could have something like where the solution curves look like hyperbolas. And when you draw the solution curve, it could be like this, say, or like this. That happens a lot too. But depending on which way you're going, if dx dt is positive and dy dt is positive, what's happening to the two populations? They're both thriving. They're helping each other out. Okay. But what happens if dx dt is negative and dy dt is negative? One of the populations dies out. Because after this is where x is 0, and the x population dies out. So that's competitive. The x population goes to 0, and the y population stabilizes to whatever that value is there. That's what it looks like when it's competitive. Okay? They're competing. They compete. They help each other out. They compete. One company wins out. It could be like companies competing over the marketplace, that kind of thing. Okay? So you get a lot of these hyperbolic type slope fields. You get a lot of these circular or cyclic, doesn't have to be a circle, some kind of cycle. They come up a lot, depending which way you go. It doesn't matter. Up the curve or down the curve, it doesn't matter really in the long term, but here the direction does matter, doesn't it? All right, so you might see some of this on the homework. Okay, so just don't be surprised by what you see. All right, so what's left is second order differential equations, 1110, 1111, and we're going to take a little break right here. So, all right, 5-10 minutes roughly, whatever, that's fine. There's 5?
Yeah, I think mutualism and competition is also part.
Competition's considered? They list that as something separate.
I think that's
Really? Okay, yeah. Well, we'll use their definition. We'll make competition separate. Huh? You do this. Mode. And then where it says float and stuff, you arrow down until you get to 4, you hit enter, you got fixed 4.
Okay.
Then all your answers get automatically rounded off to 4 places. That's all that is.
Oh,
Yeah, that's all it is. If you already have, you probably already have that, right?
yeah, I already had it.
There you go. Don't ask. The kid will kill me if I don't fix this. Yeah, well, we both play, but whatever. Well, just in case you're curious, I got the tests right here. I can tell you what's on it. Because I know the guy who wrote it from on the inside, huh? I could. I may or may not. All right. First question. Ooh, there's a big table for Euler's method. Interesting. All righty. Second question, they give you a differential equation that you can do partial fractions with to solve analytically, variable separable. The first question is numerical, Euler's method by hand, x column, y column, delta y column, for a given delta x, right? Second question is analytic, they give you a differential equation, you variable separate, you can end up doing partial fractions. Third question is what we're going to do now. You don't know what the hell you're doing. They told you what it is we're going to do. All right, so the third question is about what we're doing now. And the fourth question is competing populations we just did. Okay? That's it. Done. Wow, it was easy. 4 questions, 10 pages, just like usual. Huh? Well, the knowledge of integrating and differentiating is required. Somewhere. It'll happen. Don't worry. Let's assume at this point. All right. That's it. That's all you need to know. Wow, that was easy. Okay. So let's talk about I guess question 3 on there. How do you solve differential equations of second order? We haven't really been doing that too much. Now, you could do that. Let's see. We did that once. Look, take a look at this. What if I gave you, let's see. What if I said the acceleration as a function of time is a constant. Okay, how is that a second derivative? How is that a second order differential equation? Where's the second derivative? Acceleration is the derivative of velocity, but the velocity is the derivative of displacement. So acceleration is the second derivative, right? Okay. So let me write it that way. Whoops. Okay, hang on. The acceleration is dv dt, right? Technically what I'm saying is this. The second derivative of displacement, also known as this, is a constant. Isn't that just Galileo's free fall model without regard to air resistance? We've seen this, right? So we did it the other way around. Did we? Yeah, actually we did this one. All right, so we can figure out V, then based on V we can figure out S, and we did this. You remember this? Look, separate. dV equals negative G dt. Integrate. V equals negative GT plus a constant. We figured out that was V0, right? But then V is ds dt. And you can variable separate this. And when you integrate, you get this. Plus another constant, which we figured out was S0. Remember, we did this. So you can deal with second order differential equations by variable separables sometimes. All right, in this case, the second derivative of the displacement was the first derivative of the velocity. We figured that out first, then we got the displacement. There has to be some kind of a trick, some kind of relationship between the second derivative and the first. Okay, but what if there isn't? Here's an example. Remember Hooke's law? Okay, Hooke's law says that the force against compressing or extending a spring is working against you, and it's directly proportional to how much you shrink it or extend it. Let's say that's displacement, okay? All right. But say the spring now is hanging and is under the influence of gravity. So the natural length of the spring has to do with the weight at the end of it, okay? So I put a little weight on it, a kilogram or something, and it has a certain length. And it has a certain equilibrium, right? It's not moving. What if I perturb this thing? What if I now shrink the spring and let go? What's going to happen? The gravity's going to pull it down. But then the spring is pulling it up. The gravity's pulling it down, and bringing it up, and pulling it down. You get an oscillation. Okay. So, there's a force due to gravity, too. Let's see. Force is this, isn't it? Right? Ma? Second derivative of displacement is the acceleration. Or maybe I shouldn't have jumped that far. Okay, let me say this. According to Newton, force is always mass times the resultant acceleration. There could be several different forces, several different directions, and the accelerations are all different directions. The resultant force, right? All right, so what if I say that they're equal? Okay. Well, remember that the acceleration is the second derivative of the displacement. So then we just come up with a second order differential equation, usually written this way. How do you solve that? The second derivative is some constant times the displacement. How do you solve that? Not by variable separable. You try it. It's not going to work. So this is what I'm going to do. I'm going to say, okay, I'm after the solution to this differential equation, but let's make it easy. Let's take the easy case. What if it's just this? What if this k over m is 1? Just make it simple for a minute. Do you know any? Can you name a function s whose second derivative is its own opposite? The second derivative of s is the opposite of s. Is there no function you know like that? Yeah. That didn't happen on the recording, okay? Yeah, you didn't see that. Okay, good. Yeah. Yeah, probably. No, you know why it was? Because it didn't have a decent virus scanner and firewall and all that stuff, which I fixed. Does that have... Yeah, it is. Go away. All right, but I added all tons and tons of security, so don't worry about it. Anyway, name that function. Sine, sure. Look. Let's see. Remember when we started this chapter, we said someone solved this differential equation. They said the answer is sine. How do you check it? Well, if I say the answer is sine, like you said sine, right? Yeah. All right, sine of t, because it's the second derivative with respect to sine, right? So t. What's s prime? Just cosine. And what's the second derivative? Negative sine, isn't it? So if I replace this with this, and this with that, do I get something that's true for all t? In other words, an identity. In other words, check. Yeah, I do. Wait, is that the only function like that? What if you'd said cosine? Uh-huh. Well, then s prime is negative sine, right? And s double prime is negative what you started with. Isn't that what the differential equation is saying? The second derivative is negative what you started with. Oh, okay, so if I replace s with this, s is now cosine, so I get negative s. Is that the same thing as s double prime? Well, yeah, it is. Whoops. So there's actually two functions that fit the bill. Well, remember when we were doing partial fractions and we had 2, 3, 4 fractions? What we did was we combined them, we added them all up together. We said a over x plus b over x plus 1 plus c over x minus 2, that kind of stuff. That's when there's more than one possibility. You combine them all together linearly. That's what that means. So in other words, the solution to, forget this for 1 second, the solution to this is s of t is a times, how do I want to write this? Cosine t plus b times sine t. If this is the differential equation, this is the solution. We proved it by differentiation. That's weird. Don't we usually solve a second order differential equation by integrating twice? Well, we differentiated twice. We sort of guessed at the answer. You remember that question we skipped on the last test? Using Maclaurin's series to solve differential equations? You don't have to guess. If you did this that way, you would get sine based on certain initial conditions, and you would get cosine based on certain initial conditions. That's why that's a good question. So now I wouldn't have to guess, but all right, whatever. That's the general solution. There it is, I'm done. No integrating involved. That's the general solution to that differential equation. But wait, that wasn't what I was after. I was after this. What if it's not -1, it's negative something else? Now what's the solution? Well, I'll give you a hint. What if I write that something else as omega squared? Remember omega? That's a hint. Do you know something whose second derivative is not only negative what you started off with, but you also have a constant come out in front? When does that happen? When you differentiate and then stuff comes out? That's a chain rule, right? Can you think of a function, not cosine of t, not sine of t, something a little more complicated? So when you differentiate it, you get numbers coming out. In fact, that number comes out twice, w squared. Any ideas? A hint, it's still sines and cosines. No, it's still sines and cosines, but it's not just sine of t. No, it's still sines and cosines. What? Sine of t to the 1, no, it's not that complicated. Look, let me give you an example. What if s of t is sine of 2t? What's s prime? How do you take the derivative of sine of u? Chain rule. Cosine u du, right? Okay. What's s double prime? Negative sine u du. Well, the 2 comes out times the other 2 is 4. So whatever I started off with here, I get its squared term out here. Okay, so in other words, I just solved this. Is that the only way to solve that? No, I could have done this. Because s prime is what now? Negative 2 sine 2t. And s double prime is what? Negative 4 cosine 2t. So whatever you put here, you got its square out here, and you do get the negative s also, negative cosine u. Right? So s double prime is negative 4 cosine 2t is in fact negative 4 times what I started with, cosine 2t, or vice versa if you had sine 2t. Right? All right, let's make it more in general. What if it was not 4, but something squared? What goes here instead of 2? When this was 4, I put in 2. When this is omega squared, I'm going to put in omega. That's why I made it squared, so it'll be easy to write. Okay, so now the general solution involves omega. Omega is a constant. When you graph these functions, the number in front of the t is the frequency. So omega is the frequency of oscillation. Okay, so if this is omega t, this is omega t. Okay, so the derivative here would be negative sine u du. And the derivative here would be negative cosine u du is omega times the other omega is omega squared. So this works out. S double prime is omega squared times the original s. Likewise over here. Cosine omega t times omega, or negative sine of u du. Same thing. So what happens when one differential equation has 2 possible functions to solve it, this one and this one? You make a linear combination of the 2. So instead of writing it as k over m, I don't care that it's k over m, I care that it's some kind of constant. Okay, I'm not going to worry about this. I'm going to solve equations like this way. Well, you know what? Maybe I shouldn't just erase that. Let's leave that there. This was what? Cosine omega t. So now the solution is s of t. It's a linear combination of this plus this. So we get a cosine omega t plus b sine omega t. That's it. Done. So how do you solve second order differential equations or third or fourth order differential equations that are not separable? You sort of guess at the solution. Sorry, but that's it. Okay, go straight to the homework page for 1110. You know everything. That's it. Done. Go to page 586. Let's take a look at some examples. Like, all right, let's go to 18. 18 has like a whole bunch of questions to solve. So 18. Let's do one of these. It says The following differential equations represent oscillating springs. Which differential equation represents blah, 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 blah. I'm more interested in solving right now, so let's just solve. What if I said s double prime plus 4s equals 0, and s of 0 is given, and s prime of 0 is given? Remember, a second order differential equation, if it were variable separable, you would integrate twice. So to get the constants of integration, you would need two initial conditions, right? Okay. Now notice this is the same problem I just solved, except it's written this way. These are the same, aren't they? Same thing, just subtract this from 0, you get that. So if s double prime equals negative 4s, or if s double prime plus 4s equals 0, that's the solution. What's the solution? A cosine, if this is 4, a cosine 2t plus b sine 2t. Okay, that's it, done. Just fill this in. So s is a cosine 2t plus b sine 2t. Fine. But look, the initial conditions, what are they for? To get a and b. One of them's based on s, the other one's based on s prime. Well, so what's s prime? What's the derivative of this mess? The derivative of cosine u is negative sine u du. The 2 goes with the a. The a was there already, right? What's the derivative of this part? Plus 2b cosine 2t. Right, good. All right, now this is the general solution. I'm using this to get a's and b's, right? So I get the particular solution. So what are you going to do? You're going to plug this stuff in. What are you plugging for s? 5. And when s is 5, t is 0. What are you going to plug in for s prime? S prime equals 0 when t is 0. All right, let's fill it in. I'm going to rewrite those two equations. This is now 5. I know it still looks like s, but it isn't. Equals a cosine 2 times 0 is just 0, right? Plus b sine 0. And s prime was 0 when t was 0. What's the sine of 0? 0, so ignore this. Cosine of 0? 1. So what does that tell you about a? A is 5. What's the sine of 0? So this drops out. It doesn't tell me anything about a. Cosine of 0 is 1. So 2b is 0 means b is 0. So a was 5, b was 0. Here's your general solution. Here's your particular solution. S is a function of t. Is a, which was 5, I'm filling in this, cosine 2t, plus b, which was 0, times sine 2t, so I'm done. That's your final answer, Regis. Particular solution. Okay? That's how you solve these. It really doesn't involve integration anymore. It involves a lot of differentiation. Okay? Okay, so just remember this general solution based on omega, the square root of this, right? That's it. Simple. Do it again. That was the first one in 18. What's the second one in 18? Let's try that. The second 18 says 4s double prime plus s equals 0, and s of 0 is 10, and s prime of 0 is 0. Okay. Now who's omega? It's easy when it's 1s double prime. The omega squared is in front of s. But this isn't 1s double prime. How do I get 1s double prime? Divide everybody by 4. So what's the coefficient of s? 1/4. That's omega squared. So what's omega? 1/2. Okay, so what's the general solution? S equals a cosine 1/2 t, omega t, plus b sine omega t, which is half of t. Now, remember, for this, I need s prime. So what's s prime? negative 1/2 of A sine t over 2 plus 1/2 of B cosine t over 2. All right, plug in for S. What's the only S value we got? 10 when t is 0. So I'll do that down here. S is 10 when t is 0. Now the initial conditions don't always have to be at 0, but it's nice because things zero out. Okay. 0 over 2 is just 0. It'll still work if it's not 0. It's okay. We'll get there. And what's S prime? When t is, S prime is 0 when t is 0. All right, so 0 equals, plugging in here, negative A over 2 sine 0, because 0 over 2 is 0, plus B over 2 cosine of 0. All right, sine of 0 is 0, so this tells me nothing about B. This drops out. Cosine of 0 is 1, so A is 10. Okay, sine of 0 drops out, right? Doesn't tell me anything about A. B over 2 times 1 is 0, so B had to be 0, just like before. A is this and B is this. Doesn't always work that way, but so the particular solution is S equals 10 cosine t over 2. Compare these two solutions so far. The amplitude here is 5. The amplitude here is 10. This swings wider. The 5 goes like this, and the 10 goes like this, right? Look at this, though. The frequency here is 2, and the frequency here is 1/2. So the 10 is oscillating very slow, because the frequency is only 1/2. The 5 is oscillating really fast, because the frequency is 2. All right, that's the part A, B, C, D. Compare the solutions. Okay. I'm more interested in, can you get the solution? Can you get this? We're okay with this? Is this terrible? You just have to remember this, right? How to get this. Okay. Practice some more. What about number 3? Or Roman 3 on number 18. Says S double prime plus 6S equals 0. And S of 0 is 4. And S prime of 0 is 0. Okay. So now what's omega? It's rad 6, right? Because this when this is 1, this is omega squared, so omega is rad 6. All right, so you get S equals A cosine. Why does it do that? Cosine. Rad 6 times T, be careful the T is not in the rad, plus B sine omega, which is rad 6T. And then S prime would be what? Positive or negative? Negative. What? Rad 6 times A times sine rad 6T, right? Positive or negative? Positive. What? Rad 6 times B times cosine rad 6 times T. All right, let's plug in stuff. All right, so S is 4 when T is 0, so we get 4 equals A cos 0. I did it again. Why do I do that? There's a button on this pen that's messing things up. Hang on. All right, plus B sine 0. And then what goes for S prime? 0 equals negative rad 6A sine 0 plus rad 6B cosine 0. And this is sort of starting to get boring because all the T's are zeros and all the S primes are zeros, so all the B's are zeros. Isn't it? Is B 0 again? And A is 4? Okay, so this is getting a little boring now. So I'm not going to finish 18 because the rest is the same. So be careful though. If this is not 0 and this, if this is 0 and this is not, you're going to get sines. If they're not, if both of them are not 0, you're going to get A and B or something. One of them isn't going to be 0. Okay? So sometimes you get like 10 cosine. Sometimes you get 5 sine. Sometimes you get both, 10 cosine plus 5 sine. You know, it doesn't always have to be cosines, right? Okay, it's just fluky because of the initial conditions. You know what? You're going to see that on the homework, so save that for when you do that on homework. Question 20, for example. All right, so we can talk about that briefly tomorrow, if you're stuck on that at all. All right, so now that's the simple case, because that's not really the differential equation I had in mind. Are you ready? Now we're in section 1111, the last section of the book, I think, isn't it? I think that's it, right? We're done. Nothing else. Okay, so 1111 says, what if you have this spring, which is where gravity is working against it, right? Well, let's write it this way. Right? You have a force due to gravity. You have a total force, right? You have the force due to Hooke's law, okay? But you also have a force related to friction. I don't know what I'm going to call this. How about that? Okay? Let's say this is the total force. The force working on the spring has to do with the spring constant and some kind of friction. So the spring is in a frictional field. Think of, for example, a shock absorber in a car. Okay? The old shock absorbers used to be made out of these humongous, fat, really thick, hard springs, right? So that if you hit like a big, humongous pothole, it won't destroy the spring, but the spring constant is such that it doesn't oscillate a lot. Remember the solution? Some of them oscillate like crazy, some of them oscillate little, some of them have big amplitudes, some have little amplitudes. What kind of shock absorber do you want? Do you want a shock absorber that when you hit a huge pothole, you have a humongous amplitude of oscillation, or a nice little one? Nice little one. Do you want one that gets nice and little pretty fast, has a fast frequency, or a small frequency? We're going to have to talk about that. So I'm thinking this. I'm thinking that the motion is being, let's make it negative, is being worked against due to friction. If A is positive, I'm saying there's a negative force is working against the motion. Okay? It's like your spring is in a vat of molasses. Okay? It's slowing it down. All right? Okay? Something thick. So, now you have this situation. Notice how there's a lot of ways of modeling friction. I'm modeling friction as directly proportional to the speed. Like air resistance, right? If you walk across the room, do you encounter a lot of air resistance when you're just walking across the room? Not really. But if you fall out of a plane, there's an issue of terminal velocity because somewhere along the line, your acceleration due to gravity, the force due to gravity, will equal out the air resistance due to air friction. Because the faster you go, the more friction there is. All right, so I'm modeling the force due to friction based on how fast the thing is moving, S prime. Right? S is displacement, S prime is velocity, S double prime is acceleration. So the total force working on this spring is equal to this. The sum of all forces, right? Okay. Which I could write, I could write it this way. If I wanted to. Or I could even write it this way. Remember that K over M? There it is again. So we're still solving S double prime plus omega squared S equals 0, but there's this other thing going on. How do you solve that? That's the question. That's different. Now you got to come up with another guess. And again, if we knew how to solve differential equations with Maclaurin series, this wouldn't be much of a guess. Let me give you my guess. I don't know where it came from. You would be able to make this guess if that topic that we skipped on the last test was still in the book, okay? I'm sorry, it's a good topic, but you know, whatever. I'm going to guess, what the hell am I going to guess? Let me think. What's a good guess? Okay, I'm going to guess this. All right. Now, again, this is just some number. This is just some number. I'm going to simplify this a little bit. I'm solving differential equations like this. S double prime plus something S prime plus something S. Some constant B, some constant C, okay? It's just some number, whatever. It happens to be A over M, it happens to be K over M. It's just some number, right? I'm saying, what if we say S is e to the RT? I don't know why. Does that work? Okay, I solved it. That's the answer. Am I right? How do you know? How do you check? You plug it in, right? Okay. So I'm going to plug in this. Where? There. I'm going to plug in this for S. What do I plug in for S prime? Well, what is S prime? E to the RT times R. Okay. And what's S double prime then? E to the RT times R squared. All right, so let's write that. R squared E to the RT plus B R e to the RT plus C e to the RT equals 0. Okay. Notice there's a common factor of e to the RT, right? Factor it out. You get R squared plus BR plus C equals 0. All right, so this is true. If this is true, when is this function 0? When either factor is 0. Yes? Wait, I think you're ahead of me. Hang on. But e to the RT, remember, is never 0. If R is positive, you have exponential growth. You have an asymptote of y equals 0. If you go to negative infinity, it never becomes 0. And if R is negative, you have exponential decay. You have an asymptote of y equals 0, but it never becomes 0. This is never 0. When is this 0? Is it ever? You ever solve a quadratic equation with a quadratic formula? This is a quadratic equation in R. So you could solve it using the quadratic formula. Quadratic formula assures you of a root. So yeah, it is 0. So yeah, that's the answer. Interesting. What's R? R is going to be negative b plus or minus the square root of b squared minus 4 times a times c. But the way I wrote it, a is 1. It doesn't have to be. You could have an a here if you wanted. It'll still work. But a, so 4 times a, or 4 times 1, is 4 times c, is 4c, all over 2 times a. Well, 2 times 1 in this case. Again, you could have a number here. I usually just divide everybody by it, so it's not there. It's always, if there's a 3 here, just divide it out. So if there's a 1, okay, you could always do that. So R is that. Interesting. Well, let's see. Can we solve an equation like this? Let me give you an example. Okay, so that's the answer. That's the solution right there. Okay. Try one on for size. What if it's this? S double prime plus 3s prime plus 2s equals 0. What's the solution? Well, if we're saying that s is e to the RT, then s double prime, remember, is r squared e to the RT, right? Plus 3r e to the RT. I'm doing the same thing I did before. So there was a b here, plus 2e to the RT, right? There was a c here, big difference. The point is, you can factor out the e to the RT always, and you're left with this. So for all of these questions, you end up with what's called a characteristic equation. What's characteristic about it? It looks like this, doesn't it? 1r squared plus 3r plus 2, right? Do you actually have to do this step? Could you go straight from here to here to get the equations for r? You could, right? And sometimes it's just factorable, so you get 2 equations. Sometimes it's not, so you use the quadratic formula. Is this thing factorable? What multiplies to 2 and adds to 3? It is factorable. Okay, so r plus 2 times r plus 1 equals 0, right? R squared, 1r, 2r, 2. Yeah, that's it. This is never 0, so I'm ignoring it. So do you see what I'm saying? If I give you this, you can give me this right away. You can skip this. You can skip this. You can skip this. You can skip this, right? Now it's easy. All right, so what's r? R plus 2 equals 0, or r plus 1 equals 0. So r is negative 2, or r is negative 1. Right, good. All right, so what do we got? We've got that if s double prime plus s prime plus 3s prime plus 2s is the differential equation we're solving, the characteristic is r squared plus 3r plus 2, and r becomes negative 2 or negative 1, right? R is negative 2 or R is negative 1. But remember what we said. That's the solution, e to the RT. But R can be negative 2 or R could be negative 1. In fact, so therefore there are two solutions. Remember what happened last time when we had two solutions? Like sine omega t and cosine omega t? What did we do with the two solutions? We made a linear combination of the two. Same game. Do you see what's happening here? This is weird. When this wasn't here, when it was s double prime, not this, plus omega squared s, we had sines and cosines. But when there's something here, we don't get sines and cosines. But wait, I could still have 0 here and get r's. This somehow e to those becomes sines. Sometimes. Remember? Euler's identity, cis theta, powers of complex e, complex powers of e, gives you sines and cosines. What if the solution to r is complex? What if it's not real? Right? Remember what we're solving back here. These are the solutions we get. Do you know the 4 cases of the quadratic formula? When the discriminant is 0, you get real, rational, equal. You get like negative 1/2. That's all you get. When this is a positive perfect square, you get rational plus rational over, integer plus integer over integer is rational. Integer minus integer over integer is rational. Two different real, rational, unequal roots. Have you ever heard of this stuff? What if we're square rooting a non-perfect square, like 8? Then you have irrational answers, something plus rad 8, something minus rad 8, real, irrational, unequal. What if the discriminant, remember this is called the discriminant, what's in the square root here, right? That because it discriminates between the 4 cases. What if it's a negative number, like negative 4? What's the square root of negative 4? 2i. So you get complex roots like negative 1 plus 2i over 2, negative 1 minus 2i over 2, stuff like that, right? So how do you write this solution if there's a complex number up here? You use Euler's identity. Okay? It's going to come up real soon, all right? Now this is what? Real, rational, unequal case. The discriminant was a positive perfect square. I'm worried only about three cases. When the discriminant is positive, so this is real, rational, or irrational unequal. When the discriminant is 0, the same answer, or the discriminant is negative, complex. All right? Those 3 possibilities will mess up this answer when you get the initial conditions done. Will make this answer look different. Your final answer will look differently. All right, so let's say I gave you some initial conditions. Let's say, all right, here's some initial conditions. S of 0 is negative 1/2, and S prime of 0 is 3. How do you get A and B? What don't you have that we need? S prime. So what's S prime? S prime equals what then? What's the derivative of e to the u? E to the u du, what's du here? Negative 2, but there was an a in front already, right? So what do I get here? What should I write, plus or minus? Minus what? B e to the u, right? Because du would have been negative 1. All right, so just plug in stuff and figure out a and b. Okay. All right, so you get s is what? Negative 1/2. That's a half, okay? When t is 0, okay, so that's e to the 0 plus b e to the 0. That's nice, because e to the 0 is just 1. Okay, that's what's nice about initial conditions at 0. But it doesn't have to be at 0. You can still do it. What's s prime? 3. Again, when t is 0. So negative 2a e to the 0 minus b e to the 0. All right, so let's copy what we've got. Negative 1/2 is a plus b, wasn't it? I'm just getting rid of the e to the 0s, getting rid of that. And negative 2a minus b is 3. Is that right? Yeah, they're both negative, right? Okay. All right, so can you solve this system of equations for 2 variables, 2 unknowns? 2 equations, 2 unknowns. 2 equations, there they are, 2 unknowns, a and b. What's the easiest way to get a or b here? You could solve for b and substitute, but look, I'm thinking this might be easier. Look, aren't these opposites? How do you get rid of b and just focus on a? Just add them. 3 is really 6/2 minus 1/2 is 5/2. And a minus 2a is negative a. And b minus b is, well, it's 0. So if negative a is 5/2, a is negative 5/2. Now plug that into one of these and get b. How about the first equation? Doesn't matter. It would work the same for both. We got a is negative 5/2. So what do you get for b? What do you do? Add it. So I got 5/2 minus 1/2 is 4/2 is 2. Right? Okay, so what's the solution? A e to the negative 2b plus b e to the negative t. A is this, right? So s is a e to the negative 2t plus b e to the negative t. There is your particular solution. Did I say it? I didn't write it. Plus b, which is 2, right? Okay. There's your particular solution. There's your general solution. Okay? And that's as crazy as it gets, unless r is complex. Oh God. All right, hang on. Here's another example. Wait, hang on. All right, well, okay. Let's summarize what we got so far. If we're solving this, and it could be this, that's okay. Your characteristic equation is this. And you can solve it by factoring a quadratic formula to get r, right? Now, when we got 2 different r's, we ended up with this. Right? And they're real. They're not complex. Don't worry about complex for a minute. But what if they're the same? That's a problem. If they're the same, this really doesn't make a hell of a lot of sense. Right? Because it's just adding 2 terms that are the same. You're just going to get a plus b of the same thing. Wow. So that's the same thing as saying this. That's not two terms. I need two terms. That's a weird case. It's a special case. Okay? In cases like that, we perturb it. We change the degree a little bit. We go, let's see, where's a good example of this? Well, we don't need a good example. All you have to do is change the degree of one of these. Okay, so I'm going to do this. Instead of B, I'm saying R1 is equal to R2, R. It's like R, whatever it is, R. Okay? So A e to the RT plus B T e to the RT. I have to change the degree here a little bit. Otherwise, you're not going to get the right oscillations, okay? And there's going to be oscillations here. What you end up with here is something called, this is called overdamped. This is called critically damped. Okay? In other words, the friction is enough that it doesn't oscillate. Okay? A good shock absorber oscillates. It oscillates in such a way that the amplitude decays pretty quickly. Okay? So I want oscillation. This is not a good shock absorber. If you graph this, you get stuff like this. Big bang, and then it dies off. Okay. This is called overdamped. This is called critically damped. It's almost oscillating. It might actually oscillate. It might actually go under the axis a little bit and do like that. Okay? This is overdamped. This is critically damped. That's not quite what I want, but it's close. This is what I want. All right? Here's an example. Let's see. Is this a good example? Yes, it is. Okay. All right. Hang on to your hats. Oh boy. This is the culmination of the entire chapter. This one question. Are you happy? Are you ready? It has to do with cis theta. Okay, what if I gave you this differential equation? What's the characteristic for R? What's the equation for R? R squared plus 2R plus 2 equals 0. Good. Is that factorable? Or do you need the quadratic formula? You can always use the quadratic formula even if it's factorable, but what do you say? You need it or you don't need it, the quadratic formula? You do need it. You don't know offhand any easy factors of 2 that add up to 2. There are, but they're complex, so it's sort of hard to come up with in your head. So I'm going to say R equals, now do the quadratic formula. How does it go? Negative 2, in other words, negative b, plus or minus the square root of b squared is 4, minus 4 times a is still 4, times c is 8. Yes? All over 2 times a is 1. Remember, a doesn't have to be 1. Okay, you can do the full quadratic formula if you have a number here. It's all right. But what's the issue? 4 minus 8? Negative 4. And rad negative 4 is negative 2. So you get negative 2 plus or minus, negative 2. Rad negative 4 is 2i, so you get plus or minus 2i. And by the way, the 2 is a common factor, it cancels with this 2. I could just say negative 1 plus or minus I. So what's the solution? R1 is one of these, R2 is the other one. These are two numbers here, yes? Negative 1 plus I, negative 1 minus I. I don't care who you call R1, who you call R2. But the solution is A e to the R1 t plus B e to the R2 t. Whoops, t. And that's all you can say if you don't have initial conditions. You have a general solution. That's it. Done. Okay. But wait. Here's some initial conditions. What if? All right. Let's put it on. Let's go to the next page. So I have S equals A e to the negative 1 plus IT plus B e to the negative 1 minus IT. Right? All right. Now here are the initial conditions. S of 0 is 2. And S prime of 0 is 0. Now remember that's the easy case when t is 0, and when one of these is 0, that usually makes life easy. Okay? So I'm focusing on the complex stuff. Well, that's weird. Okay, so what do you need? You also need S prime. Okay. So S prime is going to be, how do you take the derivative of e to the u? E to the u du. What's du? Negative 1 plus I. So a times negative 1 plus I, e to the u, plus, what do you think goes here now? B times negative 1 minus I times e to the negative 1 minus it. Okay. Now this looks like a beast, and it is. But my promise to you is once you plug in the initial conditions and you apply Euler's identity, all the i's go away. Okay? Okay, hang on. Here we go. So let's plug in S is 2 when t is 0, right? So that's just A plus B, because it's e to the 0 is 1 and e to the 0 is 1. Is that okay? Okay. S prime is 0 when t is 0. So you get A times negative 1 plus I plus B times negative 1 minus I. Okay. How do you solve for A and B? Adding is going to help. I think this one maybe you probably want to solve for 1 and then plug it and substitute. Do substitution this time? Okay. So how about I get A alone? What's A alone? How do you get rid of this? Minus B. So A is 2 minus B. Okay, so wherever you see A down here, I'm going to put in 2 minus B. Okay. So 0 equals 2 minus B times negative 1 plus I plus B times negative 1 minus I. So you can solve for B. There's only B's now. The A's are not in my way anymore. All right, so what are you going to do? You're going to FOIL. Remember when we did the complex number stuff? That's why we did it. Here it is. 2 times negative 1 is negative 2. 2 times I is 2I. Negative B times negative 1 is positive B. And negative B times I is negative BI. Okay. Plus, distribute. Well, it's a negative B, so minus B. Minus BI. Okay. Now, let's see. Can we combine these things somehow? Or can we get B alone or something? Okay, what are we going to do? Look, there's a ton of B stuff here. And there's not B stuff here. Can I factor out the B stuff? First of all, these B's cancel and these combine. All right, so I really have this. Negative 2 plus 2I minus 2BI. All right, now it's easy. How do you get B alone? What are you going to do with this? You could, but I would simply add it. What are you going to do with this? Subtract it, so you get 2 minus 2I is negative 2BI. How do you get B alone? Divide by negative 2I, right? Okay. I'm going to need the next page to do that. So it's 2 minus 2I over negative 2I. That's B. Now remember how you divide complex numbers? You multiply top and bottom by the conjugate. What's the conjugate of this thing? It's simply positive 2I, right? Because it's 0. It's just positive 2I. But technically that's a conjugate. All right, so if I multiply top and bottom by 2I, the bottom becomes, that's supposed to be the easy part, 2 times negative 2 is negative 4. I times I is I squared. But what's I squared? Negative 1 times negative 4 is just 4. Okay, so the bottom is just 4. What's the top? 2I times 2 is 4I. 2I times negative 2I is negative 4I squared. Again, I squared is negative 1. So that's really a negative 4 times a negative 1 is the 4 plus 4I over 4. What happens to all the 4s? So you get 1 plus I for B? Okay. But wait. A plus B is 2. So how do you get A? Substitute what you got for B. So what are you going to do with this? What are you going to do with this? Right? All right, so here's the particular solution. It's this humongous mess where A is 1 minus I and B is 1 plus I. Holy cow. Hang on. It's e to the negative 1 plus I t. Okay. Okay, so S is stuff times e to the negative 1 plus I t plus stuff times e to the negative 1 minus I t. But the stuff is AB. Okay. A is 1 minus I, and B is 1 plus I. 1 minus I, 1 plus I. Ta-da! There's your particular solution. Huh? I thought I said all the i's are going to go away. How do you graph that? You're supposed to be able to graph this on Ziggy and see the oscillation stuff. All the other solutions we had today, you could have done that. See big amplitudes, fast frequencies, whatever, right? This is how you do it. You got to now invoke cis theta. Remember, e to the I theta is cis theta. What's theta? It's really t. E to the it is cosine t plus I sine t. That's what I'm saying. Okay? So where do I get e to the it? Do you see e to the it, just that in here? Do you see this in there somewhere? There it is. Because remember, where do you get a power made of one base and two exponents? If we distribute the t, there's two exponents here, right? All right. Keep that in mind. Look what we got. All right, hang on with me. This is about 10 minutes. We're almost done. We get 1 minus I times e to the negative t times e to the it. Isn't this times this that? Right? Because how do you multiply two powers of the same base? You add the exponents. What's negative t plus it if you factor out the t? Right? Is that the same? Are we good? Do the same thing over here. Okay? What do you notice? E to the negative t is a common factor. Let's make life easy. Take it out. But remember, e to the it, that's cis theta. And e to the negative it is cis theta with a negative theta. Okay, the sines and the cosines popped up, but the i's are still there. What was my promise? The i's are going to cancel. Why? Well, because, first of all, you know a little trig here now? Here is 0 radians, here is pi over 2 radians, right? What's the cosine of pi over 4? It's the x value here. It's rad 2 over 2. What's the sine? The y value here, rad 2 over 2. But wait, that's cosine of positive pi over 4. What's the cosine of negative pi over 4? The same x value, rad 2 over 2. But what about the y value? This is the x-axis, and below the x-axis, it's negative. Okay. So the cosine of a negative angle is the cosine of the angle. But the sine of the negative of the angle is the opposite of the sine of that angle. Do you know some basic trig identities like that? You should. All right, so what am I going to do now? I'm going to FOIL this out. Okay? Wow, I'm going to fit this here? Oh, jeez. You get 1 times that is cosine t plus I sine t. Now distribute negative I times that. Negative I cosine. What's negative I times I? What's negative I times I? Negative I squared, but I squared is negative 1, so that's 1, right? So plus sine t. Okay, this FOILs out to this. Plus, let's FOIL this out. 1 times that is that. Now distribute I times cosine. And I times negative I is again 1. So what happens? Cosine t plus cosine t is 2 cosine t, right? I sine t plus negative I sine t, poof. Negative I cosine t plus I cosine t, poof. Sine t plus sine t, 2 sine t. We ended up with from okay. Wait, is that right? Hang on, back up. What was R? What the freak is R? R was negative 1 plus or minus. Okay, that's a big difference. Okay, so guess what? This is the third case. When the discriminant is negative, the solution is e to the alpha t times a cosine beta t plus b sine beta t. You still have a constant a and b to get. It's a fluke that they're equal. They don't have to be equal. They could be 2 different numbers, a and b, right? But do you see what I'm saying? This is alpha plus or minus beta I. I'm writing a complex number in a plus bi form. Alpha is negative 1. That's the negative 1 in front of the t. Beta is what we used to call omega. The 1, not the plus or minus, just the 1. This is an absolute value always. That 1, that's the beta. That's the 1t. Okay? So whenever you get complex roots, this number goes in front of this t, and this number goes in front of this t, and you still got to get the a and the b with initial conditions, but if you start with this, it's easier to do than if you start with the complex numbers. Don't do it that way. Okay? If you get this, you write this, and then apply the initial conditions. Don't do this. You never have to do this again. Don't do this. You never have to do this again. Don't do this. You never have to do this again. Okay? All you have to do is this, and then jump all the way over to writing this with an A and a B you got to find out. Alrighty? That's it. And when you graph this, you get weird things like this. Look, you have a sine or a cosine thing with a certain frequency, and the amplitude is decaying. So it looks like this when you graph it. You have a certain initial amplitude, and it's oscillating. It crosses the x-axis, but the amplitude decays. And that's what you want your shock absorber to do, for example. Okay? By the way, you ever hear of the Tacoma Narrows Bridge disaster? You ever see that clip with the bridge starts going like this? It's one of the first suspension bridges. And it starts going like this, and all of a sudden it just blows up. The engineer who designed that bridge got a complex root here, and he said, the complex numbers, who cares? That's like imaginary stuff. Never happens. Doesn't mean a damn thing. It had to do with the stress equations on his bridge under certain stresses based on certain wind gusts. He got an alpha which was positive. Is that a good thing? No, because if alpha is positive, your amplitude doesn't decay. Do you want to be on a bridge that has an insult of some sort, a big wind, and it starts oscillating, but instead of dying down, it does this? You ever hear harmonics in music? Harmonics on the guitar, that's what that is. A harmonic on the violin, that's what that is. If you ever go on the Frog's Neck Bridge and it starts acting like a harmonic, in other words, it looks like this instead, run for your lives. Because it happened. The Tacoma Narrows Bridge disaster. That's what this is. Whoops, go away. Wait. This is good. This is bad. This is Tacoma Narrows Bridge disaster. This is 9/11. Or should have been. The World Trade Centers were built to withstand a major insult. They weren't planning on a plane hitting the top. They were planning on the earthquake shaking the bottom. I don't know if you guys are old enough to have ever been to the top. And remember, been to the top of the World Trade Center? Anybody? There used to be, I don't know, a restaurant or something up there. I was at the top. It did this. When you sat in the restaurant, at the table, you're eating your lobster, okay, and you look out the window, the city is going by you, like this, because the building is swaying in the wind. This is a design feature. This is a good thing. It's dissipating forces due to wind. This is good. If it got smacked on the bottom by an earthquake, the vibrations would oscillate out, like this, like this. Same thing should happen when the plane hit the top. Why did it all come crashing down? Why? Because the terrorists took off from Logan in a plane with enough fuel to get to California, but decided to go toward LaGuardia instead. What does that mean? There was a ton of jet fuel on that freaking thing when it blew up. And so the stress equations went to hell because all the supporting girders and whatnot, well, they melted. So all bets are off. That's why it all fell to pieces. It shouldn't have. If there wasn't that much fuel, it still would have been there. Still would be there. The World Trade Center would still be there. Anyway, so that's it. So have fun with your homework tonight. 11:10, 11:11, 11:8. All right. Let's save all this fun stuff.